Some of you may not remember, but I'll post some instructions. So you don't need to, you can come, but you don't need to go over each team. Okay, well, that's one last thing, and then you can have it, Yusuf. 1 second. Okay, any questions before we start? No? All right, let's, well, I see some prototypes. It's awesome. I think you guys are next, actually. Okay.
Okay. My team was building a modular solar disinfection system for disaster relief scenarios. Yusuf, if you could go to next slide. So when we think about a disaster relief scenario, we see that it's rather a variable problem in the sense that conditions can change rapidly, and thus necessitates a variable solution. When we think about what conditions are going to be there, there's limited electricity, reduced transportation access, and conditions are often uncertain, or we could say variable, in other words. When we now think about the people who would be actually consuming water in such a situation, we can speculate that there would be an average family of 4 people, and they consume about 15 liters of water every single day. So as the number of families increases, the amount of water you have to supply also increases. When we think about this in terms of just trying to ship water directly to that location, we start to see how, as the number of people displaced increases, the amount of water we have to ship and the logistics become increasingly difficult. Solar pasteurization offers a pathway to efficient water treatment and something that can be deployed on site. The main target, goal, or requirement of this system is that the water temperature needs to exceed or at least meet 65 degrees Celsius. We, over the course of this semester, have designed a modular solar disinfection system that takes advantage of different components to meet this goal, and something that can be deployed and scaled up to address a variety of different conditions. Jared's now going to walk you through what that design looks like in 2D and 3D space.
So this is a drawing of our 2D model. The top is the first part I'll go over, and there will be a lot of measurements I won't really go over, but you can read them. The pre-treatment module, the purpose of this module is to raise the ambient temperature of the water to increase the temperature so the rest of it doesn't have to heat it up as much. So as solar irradiance decreases, there are these green flaps that will close, which will trap the heat in. And then you'll also notice some blue lines. That is 2 layers of glass that will let UV rays through while trapping the heat and keeping it warm in there. Next slide. The next is the flow modules. These have a certain number of rows of tubing with mirrors behind them. The dotted lines show the edges of the mirrors, and the mirrors just concentrate the sun into the tubes. Next slide. And then on the right-hand side were the mirror dimensions. And here's a picture of the 3D model of what it might look like. The brown is the support structure, so metal, and the modules will slide down onto these 4 rails that are sticking straight up as support, and they'll also be able to horizontally rotate their angle to be optimally angled to the sun. And then the yellow are the mirrors, and the blue is where the water flows. And you'll also notice some of those purple things. Those are the heat activated valves that are Yusuf will go into later. Next slide.
Okay, so most of this design that we've showed here was actually based on a number of preliminary calculations. In order to actually simulate and understand this, we had to essentially construct a computational model with several different components. We start out by defining the materials that are going to be, that the system is made out of, the dimensions of this system, and then a particular date, time, and location of where this system is going to be deployed. From there, we can get 2 things. The first is the solar irradiation at that location. I believe I spoke about this in our last presentation, but essentially for any position time, we can get the irradiance at a location based on the angle of our device. We can also now initialize device dimensions, which lets us go to the next step. If you can go to the next slide, where we can essentially take the radiation that we've calculated and our dimensions and do the simulation for our pre-treatment tank, which is essentially can be approximated as being like a box cooker. And how we do this is we look at each individual component and we construct a series of differential equations governing temperature transport between them, and then solve them via approximation methods to get the temperature of the water as a function of the time and the irradiance. Next slide. From the other device dimensions, we can build our parabolic mirrors. In this class, we've covered equations for how to do that. Those are readily available online. And so based on the size of our module and the number and the sizing of our tubes as well, we can figure out what size of mirrors we can fit in there. And from there, we can get a concentration ratio or how much of the light we're actually concentrating onto our tubes. From there, we can also build our piped network and calculate things like flow rate by simply saying, okay, although it's curling in an S, we could actually just extend this to be one long tube, or rather a tube of equivalent length, and figure out what our flow and our friction factor would be from that. And that lets us get things like Reynolds number and the Prandtl number. And these govern, how heat is going to be transported to the fluid itself. Okay, last slide. Then we take the temperature that the water is at in our pretreatment tank, and that's our starting temperature that flows through this pipe system. I then use a series of analytical equations to govern heat flow from the solar radiation that's concentrated onto the pipe surface to the fluid. And that's all based on that entrance temperature. And finally, we get a temperature out, which is considered our treated temperature. Okay, now if we look at the pretreatment tank alone, we see that over the course of a day, based on that irradiation spectrum I showed, we actually don't meet our target requirements. You will see that the slope on the latter part of the day is decreased from what is initially. That's us accounting for the flaps that close and slow heat transport. Next slide. If we also then plot the flow module independently, that is, over the course of the day, we see that it also doesn't reach our temperature, but we start to see that maybe the combination of the two might allow us to reach our target. So we can go to the next slide. By combining these, we actually create an interesting operational window of when we can clean water. Right now, if we use one module, so not the two that we showed earlier, we see that we get about 5 hours where we could optimally process water and get it to that temperature. But if we can go to the next slide, if we increase the number of modules to 2, we see that our operational window increases pretty dramatically. And there is a brief window where the flow module alone is able to raise the water temperature sufficiently to the pasteurization temperature, allowing for a brief minimum amount of time where we can continuously process water. Next, Yusuf's going to walk you through what the costs of all this look like.
Okay, we started with adding some components here from the previous presentation, and as we mentioned that the most of the cost goes into making the tubes themselves. And here we have the tubes cost around 147, and we also added a support system and to the framing itself. This is to handle like different weather conditions and add support to the system. And we went about making two versions of the system itself. So the first one includes the heat-driven valves. And this adds like automation to the system. And if you don't require like any user interface, this is the option to go to. The other option would be to use manual valves and temperature sensors. If you wanna reduce the price by $500 per unit. The water storage would cost $20, and that would add to the manual version would be $950 plus shipping, and the automated version would be $1,400, and that depends on the requirements and the needs of the facility that the systems are operated into. Also, we thought about adding an option which is renting out units during fire seasons. This way, we'll get to keep the units and renting, like sending them during fire seasons, and when they're not needed over there, we can ship them back, do maintenance on them, and try to come up with the latest technology into the system. This way we can actually get to rent them cheaper for cheaper prices, but we'll get long-term rental contracts revenues over the time. And so the main difference is in the price is just the automated and the manual version.
Wrap up
Thank
there.
you.
Offer any questions.
Yeah, a few minutes is quite great. I have some questions actually, but everyone else will get a channel. Can you go to your simulation flowchart?
Yeah. Okay.
Yeah, you can go.
Can you go one forward, Yusuf? Yeah.
Yes.
So this may have not been the best way to represent
So
it.
I just want to make sure I understand. So the inputs are.
So we set up like device parameters, right? What's our materials made of? Thus their heat transfer coefficients.
Okay.
What are the
Those
dimensions?
are parameters which are not changing.
Mhm. Yeah, fixed.
I'm trying to understand what the inputs are. So you have the location and time for which you compute the variation. So to me, that what you square is the key input. And is there anything else? The water? Is it a closed system? No, it's not. Right? So you have a water tank.
Yeah. So the pre-treatment tank is where
No,
water.
the input to the water, you're assuming there's some storage before the pre-treatment.
Oh, I would assume that we're assuming that people are, I guess, filling this. Though I suppose there could be an option for that.
So that's steady state. Basically.
Yeah.
Okay. And the output you're computing is, there should be two things. One is the temperature and the second is the flow rate. Is
Yeah.
that correct? Or are you making the flow rate kind of like a.
Well, the flow rate ends up being determined based on the dimensions of the pipes.
Okay.
So we specify dimensions for the module, for instance, right? Like what it's.
Can you go to the, Jared, can you go, I think one slide, a couple of slides before?
Yusuf, could you go to Jared's drawings?
Oh, you said so. Yeah. No, yeah.
Okay, yeah, so we specify an area for that. And then we know that like the specific path that the pipe is going to take. And so based on our assumed diameter of the pipe itself, we calculate what the optimal like fit.
But there is no pump, right? It's not.
There's no pump, it's gravity driven.
So the height, so you have a specific height for the pre-treatment module, which allows you to, so that plus the diameter will determine that flow.
Yeah.
Okay.
In addition to various like friction coefficients that are calculated for bends.
Yeah. I'm assuming those are fixed basically by the materials. And, yeah, maybe there's a diameter will affect the so a little bit. But what is, I mean, how did you pick that? Right? How did you pick the flow rate? Temperature is easy. Okay, this is what you want to. What made you pick that?
Gravity.
Did you? Pick
So
that
we didn't
based
fix
on
the flow
usage
rate.
of the final product, the water. Like this
Oh,
is
so
the
flow rates actually it ends up being calculated based on just the length and the angle of the pipe itself. So
that's a design parameter. I can make it taller, I can make it bigger. But was your goal a specific flow rate, or was it just?
our goal was a specific temperature at the outlet, and thus like whatever configuration gave us that temperature, whatever flow rate demanded that.
Okay, I see. Because because the area and the area affects the power input, and the volume of the water affects how the temperature rise.
Yeah.
The mass of water.
So flow rate was more of a secondary calculation.
I see. Then how do you ensure that you have enough like water, like in a certain time period? Is it by parallelizing the modules? Like in your first slide, you had a goal, right?
Yeah.
For people, whatever. So how do you get to that?
Okay, so we show that depending on the irradiation, our pre-treatment tank will bring water to a certain temperature. We know that with certain times of day, by simply running it through, the irradiation is enough that during its path length through our flow module,
Yeah, the
it will reach its
temperature, I
temperature.
understand. I'm talking about the volume of water. Right.
Oh, okay. So, I mean, the more water you put in, right, it's going to take longer to heat up. So
are
with
you
our tank,
parallelizing the modules? Is that like,
we certainly could. This tank holds 33 liters.
and that's sufficient for whatever.
And that, so once it's in the flow process, it takes about 10 minutes for all of that to go
Okay,
through.
I see. Okay, got it. That wasn't clear to me, but now I see it.
But yeah, parallelizing them is an option.
Let's see. Oh, yeah, time. You answered it. That was my question. Okay, yeah, I think that's all I have. So my one recommendation clearly is that this should play a major role when you do the commercialization plan, because that will affect to get what is actually not only the price, but what is the how much are you creating?
Yeah,
Cost of
exactly.
water and so on.
And that's kind of where the,
Parallelization might give you cost advantages as you reduce the water. So there's a lot of interesting things to explore there.
and that was the idea behind shifting to a leasing model,
Yeah.
where depending on the situation, we can
Definitely.
send them a certain amount in a certain configuration.
National parks, by the way.
Yeah.
Okay, great, thank you. So let's
Sweet.
see, who's the next team? We're doing great on time. The hydrogen generation, Camden, Brad, Nathan. You want to use my